Last time we did the similarity transform approach to diffusion in a semi-infinite media. Today I wanted to talk about the Laplace transform techniques that could be used to solve partial differential equations. Now, earlier in the class, we used Laplace transforms to solve ODEs. We took an ODE, which is hard to solve, converted it in the Laplace domain into an algebraic equation, solved a nice little algebra problem, and bounced it back into the real domain. It turns out that that kind of approach can also be used to solve PDEs. You could take a Laplace transform of a PDE, turn it into an ODE, which is easier to solve than a PDE. You solve the ODE and you blast it back into the real-time domain. So let's do the same thing for the problem we just considered, which is diffusion into a semi-infinite media. We have some domain, boundary at x equal to 0, and the right-hand domain goes all the way out to infinity. This is an infinitely thick media. We have some drug or solute at the left-hand boundary that's exposed, and it's going to diffuse into this media and go infinitely far away out in space. We're still solving the diffusion equation of some kind of solute concentration. I've dropped the subscript A. I think you can tell what I mean at this point. So it's just some concentration that solves the diffusion equation. Now, previously, on the left-hand boundary, we had some finite fixed concentration of drug, Ca0. Now, in general, that could be any arbitrary function of time. For example, if we were to put that drug patch on our arm, that drug loading inside that patch may drop as a function of time. Or it might be a spike, a one-time pulse of an injection of drug right near the surface. And you want to look at how that drug penetrates deeper into the tissue. Therefore, that injection or the exposure to a concentration might be a complicated function of time, which I've written here as some function f as time, t. That is the surface concentration at x equal to 0. Now, the other two boundary condition and the initial condition, the two other constraints, are the same as before. Just like that. So we have a boundary condition which is now different. It's going to be some arbitrary function of time. The boundary condition infinitely far away is that there's no drug far away inside the tissue. And lastly, the initial condition, there's no drug inside the material. So these two boundary conditions and initial conditions are the same. This is the only difference. Well, now, this small little difference to the boundary condition ends up making a dramatic difference to the solution procedure, because if you try out the similarity transform technique that we showed from last time, it doesn't work anymore. It doesn't work out nicely anymore. And if you were to be given a weird boundary condition, like a Heaviside step function or a delta function pulse, it becomes really hard to handle weird functions like that. Similar to a long time ago when we were solving ODEs, and I said the non-homogeneous term, if it's weird, Laplace transform is a very good technique for solving it. Same thing here. If the right-hand side f of t is a really weird function, like a Dirac delta function with a pulse, the Laplace transform technique ends up becoming really, really effective. So let's try to solve this problem first by defining the Laplace transform of our multivariable function concentration C. We define the Laplace transform of a single variable function, like f of t, as capital F of s, which is simply the function you want to Laplace transform, f of t, slap on a e to the negative st, integrate from 0 to infinity, and that was our definition for the Laplace transforms. Now, we want to take a Laplace transform of a multivariable function. Just like that. So we want to take the Laplace transform over the variable t, time, leaving x by itself, untouched. That's going to be the integral of 0 to infinity of the concentration in real space, real time, e to the negative st dt. So you can see we're swapping out the variable time t. I'll talk a little bit later about whether we can do a Laplace transform over position. You totally can. It depends on a couple of things. I'll talk about that later. But for now, we're going to take the Laplace transform only over time and keep the variable x, which is the spatial dimension, untouched. Therefore, what we're going to do is swap the time t with the Laplace variable s. And I'm going to denote this new quantity as c bar to differentiate between the real space concentration and the Laplace time converted function c bar. Okay? So the Laplace transform of this concentration over time is c bar, which is now a function of position x and Laplace variable s. Now, what we're going to do is to go to this partial differential equation, what we've always done before with Laplace techniques. You Laplace transform the whole equation. Let's do that. You're going to come to our governing equation, Laplace transform every term inside that equation. When you take the Laplace transform of the first term, that's just the first derivative of time. So we have our handy-dandy relationship. You have s times c bar minus the initial concentration at time t equals 0. The right-hand side, this d is a constant, pops outside. The second derivative, oh, I just realized deep into this lecture that I've been messing up this diffusion equation. So you've probably been watching for like 10 minutes now, noticing, oh, that equation's wrong. That equation is totally wrong. Let me fix this. Previously, I had the wave equation. Now I have this second derivative properly installed into the right-hand side. So now we have the second derivative on the right-hand side, which it always needed to be. This is the diffusion equation or the heat equation. It's second derivative in space, first derivative in time. So I hope you guys mentally filled that 2 in there all the while you were watching this. In any case, now it's correct. We take the Laplace transform. On the right-hand side, because it's the derivative in position x, it just passes right through this definition. Because now, if you were to take the Laplace transform of the second term in second derivative in space, that just pops out. You could swap the derivative and the integration, and therefore, you just get c bar to come straight through. Just like that. So left-hand side, right-hand side, the diffusion term. But now we know the initial condition, so we can remove this term. That's just our initial condition, which is equal to 0. So the second term drops out completely. And now we have these two terms. Let's write it down cleanly. So you get this equation right here that I've boxed in yellow. Second derivative of position of c bar minus s over d, c bar is equal to 0. Now, the concentration, c bar, is a function of position and the Laplace variable s. But when you come to this point, the Laplace variable s is treated as a parameter, not as an independent variable that you need to be concerned with when you solve this equation. So the s is treated as a parameter, similar to when we did Laplace transforms earlier. You took an ODE, which was a function of time, and a derivative of time, and you converted over to Laplace domain. You got an algebraic equation. At that point, you had a bunch of s's in your equation, but you didn't think much of it. You just solved your algebra problem, treating s as if it's a constant, and you solved for your capital F function over there, or capital Y function, your Laplace solution over there, keeping s as just some parameter, and then you inverted it back. Same thing here. We're just going to treat s as a parameter. Don't worry about it, and just solve this now ODE for x. So this is an ordinary differential equation, an ODE for the variable x. So as advertised, we've taken a PDE, converted it into an ODE, which is much easier to solve. Now, this equation is very easy to solve. It's a second order linear constant coefficient differential equation. Now, it's constant because, again, s is treated as a parameter. So you can get your roots, characteristic equation, blah, 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 find our solutions. We have a second order linear constant coefficient ODE. Our characteristic equation gave us roots lambda is equal to plus or minus square root of s over d. So that's the easiest case, where now our solution is simply constant of integration e to the positive root s over d square root s x plus b, another constant of integration e to the negative square root of s over d times x. Now, all we need to do is to use our boundary conditions here and here to obtain our constants of integration a and b. Let's do that. Boundary condition number 2. Infinitely far away in x, the concentration of drug is equal to 0. Now, you need to take the Laplace transform of this. Both sides, you take the Laplace transform. In this case, this term on the left will just become c bar, because we're taking the Laplace transform with respect to this concentration. And on the right-hand side, the Laplace transform of 0 is just 0. You have to be careful here. You have to convert the boundary conditions from real space and time over to the Laplace domain. That's what we just did right here. Now, here we can plug in x equal to infinity, and you can see that the first term, e to the positive infinity, this term is going to explode. The second term, e to the negative infinity, that term will decay and go to 0. Therefore, this first term, you need to make it die. You need to kill off this term so that e to the infinity doesn't blow up on you. So that automatically gives us that a must be equal to 0 for us to satisfy this boundary condition. Good. Now we only have one term left. Let's use our other boundary condition to obtain the constant of integration b. This is our boundary condition 1. At the boundary x equal to 0, it is some function of time, f of t. You take the Laplace transform of the whole equation. Just like that, left-hand side becomes c bar, right-hand side becomes capital F of s. There we go. So we have x equal to 0. You plug it into our solution. At x equal to 0, e to the 0 is just 1. And so we have b on the left-hand side is simply equal to f of s. Just like this. And we can write down our final solution. Just like that. Here is our final solution in the Laplace domain. We have some capital F of s, which is the Laplace transform of whatever our boundary is happening over on x equal to 0, little f of t. Whatever is happening there, that Laplace transform is capital F of s times e to the negative square root of s over d times x. This is our final solution in the Laplace domain. Now, we need to invert. But when it comes to inversion, we kind of need to know what the capital F of s is. In other words, we need to know what little f of t is. Once you hand me a little f of t, I can obtain a specific functionality for capital F of s, and then I can do an inversion. Let's check the limiting case, the same case we checked last time, where the little f of t is just some constant concentration equal to Ca naught. If the boundary at x equal to 0 has a constant concentration Ca naught, then obviously the Laplace transform of that guy is just going to be Ca naught divided by s. Again, the Laplace transform of 1 is 1 over s. Therefore, this f of s would just go in here as a prefactor, and now you have to invert that. Now, if you recall the Laplace table that we've showed many, many times over several weeks ago, you're not going to find a convenient Laplace inverse and forward Laplace transform of something that looks like 1 over s e to the negative square root of s. It's not going to be on many common tables. So you have a couple of different choices. One, you can look up an even better table, a table that's better than the one I've been showing you. And in fact, there's textbooks of just entire handbooks of Laplace inverse and forward Laplace transform. So you can look up a much better handbook of Laplace tables. So just find a really, really good table. Or another trick is to use a convolution to invert. So you can take this and this, which is a product of two Laplace functions. You can do the convolution, but you need to know the inverses of each of them. And that's usually easier. You can find the inverse of whatever it is that you're looking for, and the inverse of e to the negative square root of s. That's more common. In this particular case, this problem of diffusion into a semi-infinite media is sufficiently common in science and engineering. After all, diffusion is everywhere in science and engineering. So, of course, this error function solution is going to be commonly represented in a lot of textbooks and Laplace tables. There is indeed a good table that has this inverse. So let me show you the inverse expression for this particular solution. There is an entry on a good Laplace table that looks like this. The inverse of 1 over s e to the negative a times square root of s is 1 minus the error function of quantity a divided by square root of 4t. So in this particular case, a in our solution is just going to be x divided by square root of d. Therefore, our solution is very easy. Just like that, CA naught 1 minus the error function of the similarity variable eta. Now notice that when we took this approach of using the Laplace transform, it was much easier. We didn't have to do that Boltzmann approach of first combining the right variables of x and g of t, and then finding two separate ODEs and doing something similar to a separation of variables, but then having that mysterious lambda parameter show up all of a sudden. We called that 2 equal to a constant, and then we just went forward and forward and forward, and then boom, out came the solution. But using the Laplace transform, we just skipped all of those things, went straight to an ODE, and using the stuff we learned from the first half of the course, solving this linear second order constant coefficient ODE is no big deal. We found exponential solution, applied boundary condition, and found a really good table, and boom, out came our solution. Of course, it all hinges upon having a really good table, right? Like I said earlier, misery is conserved. So conservation of misery is true. And with the Laplace transform, what you're doing is you're having an easy time early on and being miserable a little bit later on, which is the inverse. You have to be miserable at some point in your life. So if you're having an easy time now, you're going to be miserable a little bit later on. Same thing with Laplace transforms. So we had a very, very easy time here, and we skipped all those steps, just easy peasy, right? Just solving this ODE. Got to this thing, and inverting is really hard. If this inverse didn't exist conveniently on a table, we're kind of stuck. We're kind of stuck with this form here, and you can do convolution and try to massage your way forward, but you're not, you're not really guaranteed that you're gonna get a clean analytical form that looks like this. So in many situations, you can still do the Laplace transform, but you're kind of stuck with the Laplace space, and you can't, it's a hard time coming back into the real domain. So you have a couple of different techniques. You could just invert it numerically. You can take this solution in the Laplace domain, just invert it numerically into the real domain. But you wouldn't be able to write down a pen and paper clean solution analytically of C of xt looks like this. You wouldn't be able to do that numerically. The other thing is to use convolution or some techniques like that with some good tables. The third one is there is an actual definition of an inverse, Laplace inverse, using a contour integral. You need a little bit of technique using complex analysis, using a technique called method of residues. And you could use the method of residues to invert more complicated expressions in the Laplace domain back into the real space. Now, I often get questions when I'm solving this problem. Why do we always do the Laplace transform in time? Why not just do the Laplace transform in position? I'm going to answer this in a couple different ways. First, you can totally do it. In fact, you can take this ODE, do a doubly Laplace transform on space, and then now this would become an algebraic expression. You solve that algebra problem even easier than solving the ODE. But now you have to do a doubly inversion back to the real domain. Real domain in position, real domain in time. So that's like conservation of misery to the extreme. You're gonna have a very, very easy time. You're gonna solve an algebra problem, but be doubly miserable later because you have to do a double inversion, position and time. But you can totally do that. There's nothing wrong with doing that. Now, the second comment I wanted to make regarding that is there's a specific reason why we often do Laplace transform in time. And the reason why is Laplace transform is very good when you're given initial conditions at your starting point. So with initial value problems, which is usually the case with time, you're given all of your conditions at time t equals 0. And in your solution procedure in Laplace transform, it naturally comes out. In this term right here, that was your initial condition, and boom, you just set that equal to 0 so you can make progress. Okay? So in Laplace transform, a lot of times you're given some condition at 0. So if your initial conditions and all of your constraints are given at 0, it's a very, very good technique because you take your conditions here and you march forward in time. and you integrate it from 0 all the way to infinity. That's the whole point of a Laplace transform. You're going from 0 all the way to infinity. You know all of your constraints at 0, and you march forward. Now, what makes Laplace transform applied to space a little bit weird is the fact that you're usually given boundary conditions in space. You know the condition at x equal to 0, you know the condition at x equal to infinity, or x equal to L. So in position, you know the constraints at x equal to 0, right there, but you're usually given another constraint on the opposite side, either at L, a finite domain, or at infinity, out there. So then, if you were to do the Laplace transform for this problem, you're only given one of the constraints here. So as you march forward, you actually are kind of guessing what's happening on the other end. And there's no good way with the Laplace transform to see what's happening at infinity or at x equal to L. Therefore, if you're given constraints only at 0, like with the initial condition, it's very good. But if you're given one constraint at the 0 and one constraint far away, then it doesn't work out so well. What you would actually need to do is to guess a form of two of your boundary conditions in space, because it's a second order in space. You need two constraints at the origin. You would guess your second constraint, and then do a shooting approach where you guess a form of your constraint, solve it all the way. You then go to your right-hand boundary and check to see if that boundary actually matched the real boundary condition. If it didn't match, you would take that error, you would adjust your other guessed form of boundary condition and iterate over and over and over again, such that your initial guess matched and shooted to the end and matched the proper boundary condition. That sounds like a very cumbersome thing to do, so you wouldn't want to do that. But with the wave equation, the Laplace transform is very good. For example, with the wave equation, you have a second order in time and a second order in space. It's still really good technique to do Laplace transform in position, because usually with the wave equation, you have some kind of string that you're plucking, and therefore you know the initial position and you know the speed, both at the origin. Again, in time, you know exactly the displacement at t equals 0, and you know the initial speed at t equal to 0. Therefore, once again, Laplace transform in time is great because you still need two constraints. They're both given at the origin, time t equals 0, and you just march forward. And you don't know what the constraint is at time t equal to infinity, and you don't care. Because you pluck that string, it just starts vibrating, it goes out to infinity far away. You march forward in time. You know all of your constraints at time t equals 0. Therefore, Laplace transform is great at that. It just gets woven very naturally into your problem. So there's nothing prohibiting you from using Laplace transform in space. It just so happens that in many situations, x is bounded. And so when you integrate from 0 to infinity, it becomes weird because your bounds end, but you're integrating out to infinity. So even defining a Laplace transform for a fixed domain doesn't really make much sense. And a Fourier series is exactly what this is meant for. Fourier series in space is very good because you usually have periodic fixed domains. So it's a very common technique to do a Laplace transform in time and then a Fourier series in space. That's very common. For this particular case, the domain goes out to infinity, so the Fourier series doesn't make much sense. But if you have a finite domain or a periodic domain that repeats, then a Fourier series in space is the much more common technique for space. Okay, so that was a couple of my asides on Laplace transform of PDEs. A lot of students ask, why can't you just keep doing Laplace transforms? And why do you keep doing it on time? These are the reasons why. These are the considerations to make. Now, I wanted to show one last case of this problem where f of t is not equal to a boring constant, but is some weird function. For example, let's suppose that this left-hand boundary was a pulse. I have an injection, I inject it into my arm, it's a pulse, a one-time pulse, boom! A really, really high concentration of drug at one point that gets pulsed in and then becomes 0. It's not a patch, like a dermal patch where it stays on there for weeks and weeks. It's just a one-time pulse. Then what happens? Well, no big deal, because if this is a delta function, here, this just becomes a delta function. The Laplace transform of a delta function is just 1, and therefore all you would have is this is 1. The prefactor will just become 1, and all you have is e to the negative square root of s. And the inverse of that is very common. Let me show you what that is. All right. The inverse of e to the negative square root of s is so common that it's in a lot of tables that are slightly fancier than the ones I've been showing you. And it looks like this. The Laplace inverse of e to the negative square root of s is equal to this ugly thing on the right-hand side. X on the numerator. Downstairs we have square root of 4 pi d. We have time t to the 3/2 times this exponential of e to the x squared divided by 4 dt. Now we get this Gaussian function, and this form actually is quite common in science and engineering, especially if you take a class on statistical mechanics. This form is very reminiscent of a lot of things that you'll learn about ideal gases and the Boltzmann distribution. You'll get a prefactor of 1 over t to the 3/2 come up all the time, and this Gaussian form over here of an exponential. Very, very common. Now, I've coded this up. I've done my homework. So I want to show you what this plot looks like in space and in time. Once again, remember the physics of the problem. We have a delta function pulse at the left-hand boundary of a drug that's being pulsed in. One time, boom, pulse. And we want to see how that drug then penetrates into the tissue as a function of position and time. So over here, I have coded this solution. This is the same parameters that I've chosen here last time. So we're defining some parameters, the boundaries of the space, and down here, right there is our solution. Concentration is equal to this expression right here, which is identical to what I just wrote on the board. This is the solution to a Dirac delta function pulsed in at x equal to 0 as a function of position and time. So let's evaluate this. And you see, I'm plotting here concentration on the left as a function of position x. And you can see that there was an initial pulse that diffused away, penetrated into the tissue, and then slowly decays out to 0. Let's play that again. If you must blink, do it now. It's quick. The pulse is quick. Ready, set, go. So you saw the Dirac delta at x equal to 0. It quickly broadened. So that Gaussian broadened out and actually moved closer and closer and deeper into the material. And then diffusion will cause it to broaden, because you can see inside this expression, as time goes larger, the peak will just broaden. So it's like the peak moves from left to right, but also broadens. Let's play that once more. Again, it's really fast. Once more. Notice that the boundary condition at x equal to 0 is pinned to 0 the moment after the pulse is injected. And that must be the case because the boundary condition goes to infinity at time t equals 0 and then bounces back straight to 0. So that point is pinned, okay, throughout the entire duration of the animation. And of course, the boundary condition very far away is that the concentration is equal to 0. And you look at these animations and you think, yeah, that's kind of what I would expect the problem solution to look like. Initial pulse, decays down, and diffuses in. And you can really see how this kind of solution might be useful for designing drug delivery, which is the example that I gave here today, where you have some kind of pulse and you want to see how that decays. This kind of solution is also very common in electrical engineering and signal processing. You have some kind of pulse, you have some noise that pulses, or a signal that pulses, and you want to see how that pulse changes as a function of position and time. Very common, not just electrical engineering, not just chemical engineering. It's a very common phenomenon. You have some pulse, and you want to see what your system does in response to a pulse. In this particular case, we're looking at diffusion. How does a material diffuse and how does it respond to a given pulse? Okay, that's all I have. So now you are equipped with so many tools. You can do Laplace transforms to solve PDEs, not just separation of variables. You can do Laplace transforms, separation of variables. You now know about the Fourier series. You now know so much, so many tools to solve ODEs and PDEs. All right, let's end here. Next time we'll talk about a diffusion reaction ODE and PDE, and that's it. Everything that I wanted to cover in this class. See you next time.